So here's our gravitron ride. Here's our guy. He's right here. It's going to spin around. Okay. The radius, let's make the radius like 5 meters. Now I haven't been on this ride in a long time. Does anyone know about how long it takes you to go around once? Can't really tell, yeah, that's true. Alright, so we'll just use what we did last period. We just guessed 2 seconds. So we'll say it's 2 seconds for 1 revolution. Okay, so I'll put some questions up here in a minute, but let's just set this problem up. So as usual, kind of our first step should be to do our free body, right? Set up our forces. So what are the forces acting on us, on this guy? What's trying to pull him down? What's always acting on us? Gravity. So we have gravity pulling us down, right? So we'll call that Fg. Anything else? There is a normal force. Now where's the normal force coming from? The wall. Okay, so it's not the ground. We're no longer on the ground. But remember, normal force isn't just the ground. It's any surface. And so in this case, it's the wall pushing back on us. Anything else? So centripetal, so one of the things you want to be careful of, centripetal force is not an actual force. It describes some other force. So you want to look for true forces, and then we can decide, okay, which of these makes us go in a circle. Acceleration is also not a force. So acceleration is acceleration, right? How the velocity changes. It's not a force. So you think this is it? If this was our picture, what should happen to us? We should fall, right? We should fall down. So there must be something holding us up. It's not air resistance. It would be friction. Yeah, good. So friction between the wall and us is what keeps us up. Okay? So if there was no friction, if this was perfectly smooth wall with 0 friction, what would happen to us? You would slip down. There'd be nothing able to hold you up. Okay, it's kind of like if I take Mufasa against the wall. Okay, if I just let him go, he just falls. So if I wanted to stick against the wall, I'd have to push against him like this. When I push against him, there's now a normal force, and now there's some friction going up. And if this surface is slick, it's harder to keep them up. If this was sandpaper, it'd be really easy to hold them on the surface. Okay? All right, so there we go. There's our thing. So this would be the question I would probably ask you. I'd say something like, what is the minimum friction? Minimum, we'll say coefficient. And if you notice, what are the walls made like in those rides? Yeah, it's kind of like a rubbery rough kind of surface, right? Because they want to have a high coefficient of friction. They're not making it with mirrors, okay, or slick surfaces. What is the minimum coefficient of friction to stick? Okay, so we have our FPD. What should we do next? Set up our equations. Yeah, once you have the FPD, then it's kind of sets itself up from there. You just have to set up your equation. So our x equation, we do have 2 dimensions. So we're going to have 2 equations. Our x equation, how many forces do we have horizontally? We have 1, right? What is it? Normal force. And that's it. What do we set it equal to? Mass times acceleration. Do we know anything about this A? It's a centripetal A. So this is the thing that keeps us in the circle. I mean, imagine here if this guy had like a little trap door and this opens up, what happens to us? Okay, if you're in the ride and all of a sudden this door opens, what would happen? You would fly out, right? You need the wall there to keep you in the circle. If there's no wall, then you don't stay in the circle. Yeah?
What's the difference between the net force and the normal force in this situation?
Well, the net force here would be the normal force.
Okay.
Net just means the overall forces when you add and subtract everything. And since it's just this, that would be the same thing. Okay, so let's keep going. Let's go the y direction. What do we have on the y direction? So we have two, right? We have friction going up minus gravity coming down equals ma. Do we know anything about this A? Is this also a centripetal A? No. What would that mean if this is centripetal A? He's going like vertical, right? He's moving this way, vertical. So it is 0. Yeah, why is it 0?
Because there is no more than y-axis.
Yeah, we don't want to fall. Okay, so we want to stick. We don't want to go up. We don't want to go down. We just want to stick. So vertically we're not moving. So notice here what happens here is basically the question, we want to not fall. So friction should be equal to our weight. There's a balance here, right? We want those two to balance each other out. Friction should be equal to the weight. All right, so at this point you could start solving for things. Let's just derive an equation, kind of fitting it all this together and see what we get when we do that. So for example, what's our equation for friction? Mu times F normal. What's our equation for gravity? Mass times little g. Mu Fn equals mass times little g. Okay. So I just expanded these two, right? Normal force, is this just mg like it is 90% of the time? No. It's only mg when you're like on a flat surface, right? Do we know anything about this normal force? Okay, yeah, we found something about it right up here, right? We said the normal force was equal to mass times the centripetal acceleration. So what we're going to just do is go ahead and substitute this in. Now if you're not comfortable with what I'm doing, you can always calculate stuff as you go. But let's just do it all at once. So we're going to have mu times mac equals mg. Masses cancel, right? So if you're an engineer of this ride, do you have to worry about little kids getting on your ride? No, because the mass doesn't matter, right? Mass doesn't matter. All right, what were we solving for? Mu? Let's expand AC. What's our equation for AC? V squared over r equals little g. And therefore mu should be equal to, if we multiply both sides by r and divide by v squared, mu equals rg over v squared. Again, if you're not comfortable with what I'm doing, you can kind of substitute numbers as you go and solve for things as you go. All right, so we are looking for mu. I gave you r, right? And g we always know. Do we know v? How can we calculate v? V equals d over t, exactly. And what's the distance if we're going in a circle? Okay, the circumference, 2 pi r, good. So let's find out how fast we're moving in this example. Pi times 5? About 15-ish. 15 point.
7.
So that would be our speed, how fast we're moving. Right? So then we'll just go ahead and plug that into our mu equation that we derived earlier. So R was what, 5? Little g, 15.7 squared. Looks like it's a lot less than 1, yeah? 0 point something. 199. So that's the minimum coefficient, right? So if you're an engineer, you wouldn't do the minimum. Why wouldn't you do the minimum? Okay, yeah, someone comes in with like a slick jacket or something, and all of a sudden they're going to fall. So you would make it a lot higher, okay? And those walls that you saw were probably like 1.5 or something, their mu's that they had.